Evet arkadaşlar, kaldığımız yerden devam edelim. So we have this theorem. Let f and g be functions. Phi and psi one forms, and a and b real numbers. Then we have the followings. Then a is d of a times phi plus b times psi is just a d phi, b d psi. So exterior derivative is a linear map from one forms to two forms. It also satisfies Leibniz rule, namely exterior derivative of the product is just g times df plus f times dg, and 3 is okay. So f times a one form is again Leibniz rule df times psi, but since these are now one forms, here we use, of course, wedge product, and then we have plus f times the psi, and the the fourth one, if we have wedge of two one forms, then the exterior derivative is just the exterior derivative of the first one times the second. But now, since this is a one form, we have a minus sign, so it is like this. Okay. Let's talk about proof of, well, first one is kind of easy. The second one is also easy, but let's do that. So it is d of f times g. So what is this? This is by definition partial derivatives of f times g, dxi and dxi. Well, so this is dfg is, and here we apply Leibniz rule. So this is just del f del xi times g plus f times del g del xi, and then dxi, and we can group these as follows. So I have here g, common term. I can take it outside, and here we have I from 1 to 3, del f del xi dxi, plus this time I can take f outside, and we have 1 to 3 del g del xi dxi. But you see, this is just g times df plus this is f times dg. Okay, so this proves the second one. Let me talk about number 3. So number 3 is this: d of f times phi. Okay, now let's say phi has the following form. So I want to show that this is equal to df times phi plus f times the phi. Now take phi to be this gadget. It's a one form. So any one form has the following form. Let's say AI times dxi. AIs are just some functions. Okay. So what is d of f times phi? So this is just d of sum from 1 to 3 f times ai dxi. All right, I can take the summation outside, and then d of this expression. I have a function here times dxi. By definition of the exterior derivative, this is nothing but d of the function, exterior derivative of the function, times dxi. Okay, now what is this exterior derivative? Well, it is another sum. So let me write it this way. This is I from 1 to 3, and then we have, let's say, j from 1 to 3. What is this gadget? This is just del of f times ai del xj dxj. So this is the exterior derivative of this expression, which dxi. Okay, so that is equal to what? Summation over I and j. I may write it this way, and then exterior derivative, partial derivative of f times ai with respect to xj. I can apply Lightness rule here. So this is just del f del xj times ai plus f times del ai del xj. Yes, so this is the partial derivative of f times ai with respect to xj, and then here we have dxj, which dxi. Okay, well, okay, I want to show that this is equal to this expression. So I should either, okay, here I have the f term. I can pull out the f terms here. So this is f times ij from 1 to 3 del ai del xj dxj, which dxi, plus the other terms I from 1 to 3 ai times, or okay, del f del xj times ai dxj, which dxi. All right, well, note that I can write this as follows. This is f times, and then I have here I from 1 to 3, and then we have here j from 1 to 3 del ai del xj dxj, and then here I have which dxi, plus this expression. Here I can write something similar. Here we have j from 1 to 3. yes, del f del xj dxj, and then which ai times dxi. Here I have, of course, summation also from 1 to 3. Okay. Well, here note that this expression here is nothing but actually d phi, right? Because phi is this expression. What is the exterior derivative of this? You take partial derivatives of this with respect to j, dj, and then you multiply with this gadget. So this is just f times I from 1 to 3, and then I have okay. Yeah, maybe I can do this as follows. Let me keep this and compute the right hand side. Okay, let me erase the theorem, statement of the theorem, and let's compute the other part and see if they are the same. Okay, let's do it that way. Yeah, maybe I can just put it here, and then, okay, let me stop here and compute the other part. Let's see what we get. So what is the other part? I have computed this. Now let's compute this too, okay? And see if we get the same thing. So df wedge phi. What is df? Okay, for f I use j notation. So let me write this. df is just j from 1 to 3 del f del xj dxj wedge. So this is the df wedge phi, and phi is just this expression. Instead of phi, let me write this: I from 1 to 3 ai dxi. So if I combine the two, we get summation over I and j. And then this is a function. I can just take it here. So this is ai times del f del xj dxj wedge dxi. And note that this expression is the same as this one, right? So, okay. So this gadget here is exactly this one. All right. Now let me, so it is this one here. Now let's compute the other one. Okay, this one. Let's see what it is. F times d phi. So F times d phi, F times d of phi is just ai dxi, I from 1 to 3. Right. So what is the exterior derivative of this? 1 to 3. I will take just exterior derivative of this gadget. So it is just d of the coefficient function dai wedge dxi. Okay. Well, a is a function. So its exterior derivative is what? It is equal to the following: j from 1 to 3 del ai del xj dxj wedge dxi, and this is nothing but, so summation from over I and j from 1 to 3, I have f times del ai del xj and then dxj wedge dxi. So you see this expression here, is equal to this, and it is exactly this one here. It is exactly this one. Therefore, you know, this expression here is equal to the summation. All right, so this proves number 3. For number 4, one may proceed as follows. Let me just write down a couple of things. Okay. I will not maybe finish it, but let's just write some of them. Okay. All right. So part 4 was this. D of this form is equal to d phi wedge psi minus phi times d psi. All right. Now, again, let phi to be ai times dxi, and this time let psi to be, let's say, bj times dxj. Okay. Here's summation from over I, and this is over j. First, I have to compute the product. So phi times psi, the wedge product, that is just summation over I a dxi wedge j bj dxj. So this is just summation over I and j, ai times bj. This is the coefficient function, and here I have dxi wedge dxj. Okay. So it is this gadget. Well, we have to take d of this gadget, and also we have to compute, you know, these 3 terms, and then we have to just compare, you know, all of them. So, okay. So what is d of this expression? D of phi times psi will be just d of summation over I and j, ai bj times, okay, times dxi wedge, no, dxi, yes, wedge dxj. All right. Well, this is nothing but, since this is a form, I will take, the exterior derivative of this and then wedge with the form here. And d is linear, I can take it outside, d of ai times bj, and then wedge dxi dxj. So what is d of this gadget? Well, this is another sum. So I have ij and then summation over k del ai bj over del xk dxk wedge dxi wedge dxj. Okay. Well, this is what, this is just summation ijk ijk, and then partial derivative of this. This is just del xi del xk del ai del xk times bj plus ai times bj del xk. All right, and then dxk wedge dxi wedge dxj. All right, so the left hand side of this equality is equal to this expression. Now let's compute the right hand side also and see if they are the same. Okay. All right, so let's compute d phi wedge psi, d phi wedge psi. So what is d phi? D of phi. Phi is I ai dxi times psi. This is just j, summation over j, dxj. All right, so what is d of this? D is linear, I can take the summation outside, and then d of xi, d of ai, and then wedge dxi. All right, wedge product, summation over j. All right, now what is d of a function? D of a function is a sum, let's say over k del ai del xk dxk wedge dxi, and then wedge bj dxj. Here I have three summations. I can combine all of them here, and then we have the coefficient function del ai del xk times bj. Since these are functions, zero forms, I can just take them wherever I want. And then what is left here, dxk wedge dxi wedge dxj. Now let's combine, let's compare this with this expression. Okay, so I have del ai over del xk bj dxk dxi dxj. So I have this part here, this gadget times this summed over ijk. So it is exactly this. Okay. So we obtained the first part of this. Okay. First part of this summation. And as you might guess, you know, the similarly, phi times deep psi will be what? So phi is AI dxi, which d of psi j bj dxj. So this is just summation over I, AI dxi, which d of this is just summation over j dbj times wedge dxj. Since this is a one form, I have to take wedge product here. So we have summation over I, AI dxi, wedge, summation over j. And then what is this? This is just another summation over k. Let's say dbj del xk dxk. And then wedge with dxj. I can write it this way, okay? Well, I have what? This is just summation over ij and k, ai times del bj del xk, and then we have dxi, dxk, and then dxj. Let's compare this with this one. Okay. AI del bj over del xk. Here I have dxk, dxi, dxj. Well, it is not this expression, right? Here I and j should be interchanged, and I can do this. So this is like changing the place of two rows in a determinant, right? These are one forms. When you switch them, you pick up a minus sign. So when I switch these two, if I write k here and I here, then I have to pick up a minus sign, and you see that this is exactly what we needed, because I have another minus sign here. So if I put a minus sign here, I have a minus sign here, another minus sign here, and that minus sign will make it plus. So when it becomes plus, you just get this plus term, okay? So this proves the fourth part of the theorem. Okay. All right. What else do we have? Well, this finishes the section 1.6, differential forms. Now let's talk about differential mappings. Okay. So that's the next section. Okay, let me erase also blackboard here. All right. So I have a couple of definitions. The first one is this. Given a function f from Rn to Rm, let f1 up to fm denote the real functions, the real valued functions on Rn. So they are functions from Rn to R such that they fit into this equation. F of p is just f1p and so on up to fmp. So this little f1 to fm are nothing but the coordinate functions of f for all p or n. In this case, these fi's are called the Euclidean coordinate functions of f, and we write in this case f equals f1 up to fm. Okay. Another definition, if I from I into Rn is a curve in Rn. So if here I is, of course, is an interval in R, an interval. So if this is an interval, a function like this is called a curve in Rn, and f is the above function, so is a function from Rn to Rm, is a mapping then the composition beta, which is just f composition alpha or f of alpha. So from this is a function from I into, I go first with alpha and then by f, so into Rm is called is a curve in this time of course in Rm called the image of alpha under F. All right. I have one more definition. Since we are learning a new subject, we have to go through lots of definitions. This is typical. Okay, whenever you start something new, a new subject, you have to first learn the concepts, tools, and then you start building the theory. But first we have to go through all the definitions. All right, so let F be a mapping if V is a tangent vector, V or VP is a tangent vector to Rn at P, let F star V denote be the initial velocity vector of the curve parameterized by T as follows. So T goes to P plus TV. So you are at the point P. This is in Rn. You are at the point P, and you consider the line through P with vector V. Okay, so you just V is a vector like this. So P plus TV is this point, and you talk about the velocity vector of this curve. So that is nothing but how would you compute the velocity vector of this? Velocity means if this is a curve, it is just the t derivative, right? So it is just d over dt of f of p plus tv. I take derivative of this with respect to t and then compute it at t equals 0. So what happens is the following. You go by f, so you obtain a curve like this. Let's say this is the point f of p, and the velocity vector is this. So that vector is just f star of v, okay? It's a tangent vector at the point f of p. Okay. All right. So, okay, the map f star from from the tangent space to Rn at the point P to the tangent space at Q to Rm, taking V to be f star of V. So this is the point. Q is the point f of Q, okay? It takes the tangent vector at the point P and sends it to a tangent vector at the point Q, okay? This map is called the tangent map is called the tangent map of f at p. Okay. All right. Let us stop at this point. So next time we will see how we can compute the derivative map in terms of the coordinate functions of f. All right, so let me stop. I'll see you on Monday.